Modern machine learning models, like those powering next word prediction and facial recognition, require massive datasets to function accurately. Historically, this meant vacuuming up user-generated data from millions of local devices. The traditional approach to distributed machine learning relies on centralizing that information. The system physically extracts raw data from smartphones and laptops at the edge of the network and transfers it to a centralized computing facility to train the model. This architecture creates severe technical friction. Moving petabytes of data over wireless networks causes extreme latency and high bandwidth costs. Furthermore, aggregating personal messages and location histories into a single repository creates a massive target for data breaches. Many industry standard practices assume that stripping explicit identifiers like names or relying strictly on aggregated statistics like averages provides adequate protection for the individuals inside those databases. However, data centralization is no longer a viable strategy. Even supposedly anonymous, aggregated datasets remain vulnerable to sophisticated mathematical deduction. To safely build machine learning systems on sensitive information, engineers rely on a zero-trust architecture achieved through two specific technical requirements: differential privacy and federated learning. Differential privacy is a mathematical framework for data obfuscation. It precisely quantifies and limits the exact amount of personal information that an algorithm can leak during computation. Federated learning is a decentralized optimization system that inverts the traditional training pipeline. Instead of moving the data to the computation, it moves the computation directly to the data. Federated learning eliminates the physical network bottlenecks and bandwidth costs associated with centralizing data. Differential privacy addresses the mathematical vulnerability of the aggregated outputs themselves. By combining these two methods, engineers can train global predictive models that learn from millions of distributed devices without ever exposing a single clear-text data point to the central server. To understand why aggregated statistics fail to protect privacy, consider a linkage attack. This occurs when an adversary queries a database to extract an average value without seeing individual records, then uses sequential queries to reverse engineer private data. At the end of January, a standard database query reports exactly 100 employees with an average salary of $55,000. 1 month later, in February, a second query reports 101 employees, and the average salary has risen to $56,000. The company has not released any names or individual salaries. Yet, the exact compensation of the single new employee can be deduced using basic arithmetic. First, you calculate the total January payroll by multiplying the 100 employees by their $55,000 average, yielding exactly $5.5 million. Next, you calculate the February payroll, multiplying the 101 employees by the new $56,000 average yields $5,656,000. Subtracting the January total from the February total isolates the exact salary of the 101st employee, revealing they are paid exactly $156,000. Releasing accurate aggregated statistics provides no mathematical guarantee of individual privacy when an adversary can run sequential queries over time. Differential privacy prevents the linkage attack by injecting carefully calibrated random noise directly into the aggregated outputs. A differentially private algorithm alters the true values. Instead of 100 employees, it reports 103. Instead of a $55,000 average, it outputs $55,500. When an adversary attempts the exact same subtraction method using these noisy aggregates, the individual calculation yields a meaningless number. The effectiveness of this protection relies on a metric called sensitivity, which dictates exactly how much noise the system must inject to obscure the data. Sensitivity is defined as the maximum possible impact a single individual could have on the function's output. To be secure, the algorithm must add enough noise to obscure the highest possible salary paid by the company, not just the average. This creates a strict engineering trade-off. Injecting too little noise leaves the data vulnerable to reverse engineering. Injecting too much noise destroys the statistical utility of the dataset entirely. While differential privacy successfully secures statistical queries, training full machine learning models requires processing vast amounts of raw data. To do that securely, the system must prevent the data from being aggregated centrally in the first place. Federated learning bypasses centralization by having the server broadcast the initial global model parameters, the weights, directly to the edge devices. Weights are the internal numerical values a model uses to make predictions. A central server coordinates the training process alongside 3 active edge devices: Mobile 2, Mobile 3, and iPad 2. Data is heavily unbalanced across these devices. Mobile 2 holds 20 data points, Mobile 3 holds 30, and iPad 2 holds 200, totaling 250 active data points. Mobile 2 begins local training using stochastic gradient descent. It updates the model's parameters by calculating the error on small subsets of data points. Processing its 20 data points in batch sizes of 10, Mobile 2 completes 2 distinct gradient updates. Simultaneously, Mobile 3 performs 3 updates based on its 30 data points, while the larger dataset on iPad 2 drives 20 distinct gradient updates. Throughout this process, the raw browsing data remains permanently locked on local storage. The devices transmit only the updated model parameters, the optimized weights, back to the central server. Executing the computation on the edge device utilizes the private data without ever exposing it over the network. However, it leaves the central server with a set of heavily skewed, unbalanced model updates that must now be mathematically reconciled. To combine these disparate local updates into a single, cohesive global model, the server relies on the federated averaging, or FedAv algorithm. The server cannot treat the incoming updates equally. A simple average would give undue influence to the sparse data from Mobile 2 and dilute the rich patterns learned from the extensive dataset on iPad 2. The server calculates the exact proportion of data each device contributed to the total pool. Mobile 2's 20 data points represent 8% of the total. Mobile 3 contributed 12%, while iPad 2 provided the vast majority at 80%. The server then scales each device's submitted weight matrix by its data proportion. Multiplying Mobile 2's weights by 0.08, Mobile 3's by 0.12, and iPad 2's by 0.80 yields the exact parameters for the new global model. FedAv dynamically accounts for data heterogeneity. Devices with richer datasets proportionally drive the optimization of the global model, extracting maximum analytical utility while keeping the raw data isolated at the edge. Unlike controlled data centers, real-world edge environments are hostile to distributed computing. Mobile devices suffer from battery drains, limited wireless bandwidth, and unpredictable offline periods. Federated learning handles these hardware constraints asynchronously. If a mobile device loses its network connection mid-training, the server simply excludes the missing device and aggregates only the updates it successfully receives. With the new global model calculated, the server initiates the next communication round by randomly selecting a completely new subset of available devices, bypassing the original 3. Because transferring neural network parameters over wireless networks is expensive, communication costs dominate computational costs. Engineering efforts focus on minimizing the total number of communication rounds required for the model to reach convergence. This asynchronous client sampling ensures that the entire global network never bottlenecks on a single disconnected or underpowered mobile device. Across a single training round, the global model successfully learned complex behavioral patterns from 250 distinct data points, without the server ever processing a single piece of raw data. This dual architecture mathematically bounds privacy risks directly at the edge of the network, while still extracting precise analytical utility at the center. Combining the precise noise calibration of differential privacy with the decentralized network topology of federated learning establishes the required standard for modern, secure machine learning. This new approach reorients the engineering focus. Instead of simply scaling up centralized data repositories, the goal is now optimizing communication efficiency across millions of distributed edge nodes. Zero-trust machine learning proves analytical power does not require centralization, ensuring future systems scale globally while preserving the mathematical right to individual privacy.